Now consider the Miller's theorem. What is the Miller theorem? The statement is an impedance Z connected between the input and output section can be replaced by an impedance Z upon 1 minus A at input side and ZA upon 1 minus Z at the output side, where A is the voltage gain. A is the voltage gain. Now, the proof, for proof, let this is the impedance Z. This is the impedance Z connected at the terminal 1, 2 as VI input terminal, and this is P4 as output terminal. So as per the Miller's theorem, this can be replaced by Z 1 minus A Z upon 1 minus this at input impedance, and then as at output impedance ZA 1 minus A. This is the terminal V input, and this one is V output, and here it is, say, current I1 is flowing and this current is I2 is flowing in the circuit. So this is the first circuit, that is A, and here it is the second circuit as B. So suppose current I1 is flowing in the input terminals then this I1 is equal to Vi minus VO upon Z. So take VI common. This is 1 minus VO upon VI upon Z. So this is VI 1 minus A upon Z. So this is VI upon Z upon 1 minus A. And this is VI upon ZI. This is I1, where ZI is equal to Z upon 1 minus A. 1 minus A, that is ZI is input. Where A was V0 by VI gain, voltage gain. Similarly, for the output terminal, now consider the current I2 in output section, that is I2 is equal to V0 minus V1 upon Z. So we have, this is V0 upon V0 by gain. This is the value of VI. This is VI upon Z. So V0 take common, that is 1 minus 1 upon A upon Z. So this is V0 upon Z divided by 1 minus 1 upon A. 1 upon 1A. So this can be written as V0 upon ZA A minus 1. ZA A minus 1, or this is V0 by ZO, where ZO is equal to ZA 1 minus A. ZA 1 minus A or A minus 1. This is I2 with this sign. So this I2 is equal to minus V0 A Z 1 minus A. And this is your Z output is ZA 1 minus A, the output impedance. This shows that the current I1 and I2 are in opposite directions, in which the given network have the different input and output impedances. So that is your Miller theorems. This is all about your Miller theorem.